Very good. All right, so I will just start. Okay, type of stimulation. I usually when I give a class to next training, Schlumberger or to IATMI, or during that 5 days, is a lots of topics covered, but I try to give some introduction here. I will say, right? I mean, on fracturing for your basis to understand what is a fracturing in the oil field industry, because the 5 days usually you go down detail on the fracturing geometry optimization, what is the best frac length, width, and everything, and as well on the data frac analysis or mini frac analysis. We're not gonna cover that today, right? But at any time later on, when we have time, then we can always have a special class for that, right? So it's a 5 days course, and these 2 hours we have today, 1 hour, 2 hours we have today is an introduction to that, okay? So mainly we have a type of stimulation, introduction on why we do fracturing other than fun, and 70 years frac history. What will you see in the problem, and then you should be fine just running things to clean it up, right? It could be just, if it is wax, you run mutual solvent or surfactant. If it is scale, you run acid or anything. And this is like, how do you run this? Usually most of the time is 1.5 tubing volume, okay? So if your tubing volume here is, let's say 200 barrel, then you circulate 200 times 1.5, which is 300 barrel to the surface, right? You circulate down to the bottom. You can unset the packer and then circulate through tubing, through annulus, or just use a coil tubing is even better, right? Now, move to the matrix treatment. Matrix treatment, the number 2, you actually treat it anything around the wellbore here, okay? So somewhere here, not too far away. So on the matrix treatment here, matrix treatment usually is a pumping rate is less than the frac rate. So you never part or break the rock with the matrix treatment, right? So your pumping may be, I will say maybe 2 barrel per minute. Okay. On matrix, the area of penetration is at critical wellbore radius, penetration. Maybe anything between 5 to 15 feet. All right. So that's when you have a matrix treatment, okay? And matrix treatment is usually you are running the matrix treatment is for high permeability reservoir, okay? High perm, you don't really need you don't need to improve your conductivity, then you run the matrix treatment. All right, so the number 3 now, which is what we are going to discuss today, is fracturing. You guys still can see? All right, good. Fracturing is divided by 2. 2 types of fracturing. Number 1, let me just move this one here a little bit. Number 1 is acid fracturing. You're pumping acid at a high rate, acid frac. Number 2 is propan frac. So instead of using acid, you are using propan. So propan is a sand. It's a sand material, right? But it's a man-made sand. We call it propan. So there are acid frac and propan frac. So what's the difference with matrix then, other than the material? With the fracturing, we are pumping at high rate, high pumping rate. So then we break the rock, right? And plus 100 feet away, maybe you cannot see that. Long penetration. long penetration. Penetration half length is XF. When you talk about half length, we call it XF, right? So long XF, half length. Maybe 100 feet. It could be 1,000 feet from the wellbore, very far away, all right? So that is fracturing, my friend. Anybody has any questions so far before I continue with the slides? All right, let's go back to the slides. Can you see my slides? Pause.
Yes, sir.
All right, very good. Okay, so go back again. We have wellbore cleanup, we have matrix treatment, and we have hydraulic fracturing, okay, which is divided into two, acid and proppant fracturing. Let's move on. Now, there are many ways how we want to clean this, do this fracturing, right? Somebody draw my screen, it's okay. So anyway, so we have, this is the permeability, this is the reservoir quality. When you talk
Excuse me,
about
sir.
reservoir, yes?
Sir, please off the annotation.
Hmm?
You'll be getting an option on your screen to switch off the annotations.
Annotate here.
Yes, sir. So no one will be able to draw.
Okay.
Yeah.
It's okay. If they want to draw, they draw. I'm fine.
I request
That's fine.
participants.
All right. So that's okay. All right, guys. So anyway, let's continue. Okay. So again, the quality of you guys from the petroleum background, right? So you understand permeability
Yes,
or not?
yes, sir.
You heard about permeability. All right. So permeability is the ability of the rock to transmit the fluids, right? So then the higher the permeability, we call it the better the reservoir is, the reservoir quality, when the permeability is higher, right? What is higher here? So if you talk about the US tight gas is defined as anything below 0.1 millidarcy, all right? So anything below 0.1 millidarcy, which is this one here, okay? Anything less than this is tight. In US, they call it tight gas, right? So then, tight gas is anything below. If you're in Europe, Europe definition on tight gas is 1 millidarcy, right? So anything less than 1 millidarcy in Europe is called it tight. So 0.1 or 1 is a tight reservoir, right? So above that is you can call it medium permeability to high permeability. All right, so there is a permeability and there is porosity. Of course, porosity is the pores of your reservoir. The higher the permeability, theoretically speaking or logically speaking, then the higher the porosity is, right? Now, what type of stimulation can you apply based on this reservoir quality rock? So if you deal with a very high permeability, maybe anything above 100 millidarcy, then you may want to apply matrix stimulation, as you can see from here, right? So matrix stimulation here, excuse me, matrix stimulation is for the high permeability. You can apply whether it's a sandstone or carbonate. Then if you are in the medium to high permeability, you still can do fracturing for the high permeability, which is we call TSO. Here, you call it TSO here, tip screen out. Then after that, when you deal with start entering the low permeability region, then you start applying a massive frac. Massive frac is a long half length XF. Again, XF is a half length. It's a long frac. All right, aim to reach to go deeper to the reservoir and then improve your reservoir contact. And last but not least, which is we are on the way to there with the shale gas and shale oil frac initiated in US, Barnett Shale, then you are in the marginal economy and then you are approaching nanodarcy formation or reservoir, right? It's good. Let's continue. All right. So this is new for me. I need to erase. Right. Okay. Good. All right. So again, this is just to show that this day you are going for the deeper, hotter, more difficult reservoir. So the high medium quality reservoir is gone many years ago, right? So we are now in the process of going to the tighter and deeper reservoir, and is more difficult to as well extract, right? So now let's spend some time here. You guys can see equation here. Don't run away. Stay here. Can you see the equation?
Yes, sir, we can see.
Okay, what equation is this? Start with you, Horse.
Sir, introduction to fracking Q equals to.
What question is this? Equation. What equation is this? Q is equal to K times height times delta P divided by mu O B O ln RE over RW plus skin. This is Darcy equation, all right? So let me check.
Yes, sir.
Yes, so this is Darcy equation. Q is oil rate or gas rate, all right? So there is actually here, there is A constant. Q is a hydrocarbon rate. It can be either oil or gas. That is Q. K is permeability, the ability of a rock to transmit the fluid, right? Height is H is the height, the reservoir height. This is the H. Multiply with reservoir pressure, which is the pressure inside reservoir that push the fluid to the wellbore, minus PWF, which is the bottom hole flowing pressure, divided by mu. Mu is your reservoir fluid viscosity. B is formation volume factor, and ln RE over W plus skin. All right. Before I continue here, guys, so raise hand and then let me know if anybody know what is skin. You raise hand. If anybody know, raise hand. Hello? Host? Can you check if anybody knows what is skin here and then they raise their hand? Okay, so Anus,
Yes, sir. None.
Anus Batia, go ahead, Anus. What is skin?
Skin is the dimensionless factor that determines the damage around the wellbore.
All right, when the skin is positive, what does it mean? Nandini, go ahead.
Yes, so when the skin is positive, that means there's a damage around wellbore, so that is not good for us. But when the skin is negative, that is good for us.
All right,
So
very good. Now, what's next here? When the skin is zero, what does it mean?
that the wellbore is exact size that it's supposed to be. So the positive skin means that the wellbore has reduced radius, and negative skin means it has extended radius.
So when the skin is zero, it's neither stimulated or damaged, right?
Yes.
All right, very good. All right, so let me continue now. So this is the skin. When the skin is positive, as been explained by Nandini, when the skin is positive, then the well is damaged, reservoir is damaged, the wellbore is damaged, and the Q, because this skin is positive, the Q here is reduced, right? When the skin is negative, the Q here will go up, right? So now, if you look at the plot on the left side here, there is a relation between skin and FCD, right? FCD is dimensionless fracture conductivity. You can see on the left side on the vertical axis here, this is a representative of the skin, right? And you can see that on the bottom here is the number, dimensionless fracture conductivity number. All right. So don't worry. If you don't know what the FCD is, I will explain later. But look at the plot here, guys. If you look at the plot here, the higher the FCD, the more reduction in skin. All right. So we want to have a higher FCD, so your skin is going low and perhaps it could reach a negative number. All right. So now the biggest drop is coming from the FCD of 0.2 down to FCD around 2. So this is the steepest slope here, right? In the very early part of the slope from 0.2 to 2 on the FCD. Then after that, there is a slightly steep here to FCD of 10 or maybe 20, if you want to call it there. And then from FCD 30 maybe down to FCD 1000, the drop in skin is not that much, all right? Now, what is FCD here? FCD is dimensionless fracture conductivity, and this is the equation of it. Dimensionless fracture conductivity, we have proton permeability times fracturing width. Let me just move this bar here. So proton permeability is the material, the sands permeability, the sands that we are pumping to fill up the crack that we created down there, multiply with the frac width, and divided by formation permeability times fracturing length. So if you look at the cartoon here, so when we apply, if you look at the cursor here, when you apply a pressure and then crack the rock then will start to open here to be cracked. When the rock is cracked, then it's created a width. All right? Can you see my cursor here? This is your width. Then the crack is continued. And the width is open and open along the half length. So this is from, if this is your wellbore here, from here to here is your half length. Okay? And this is your width, your crack width, and the crack has a length, right? So this is what shaped the FCD equation. A proton permeability, which is the sand material, the sand has permeability. You multiply with the fracturing width divided by formation permeability divided by fracturing length. Okay, so let me just switch to the screen. All right, so let me just slowly here. I will explain what is the FCD concept. Right. So FCD is equal to propan permeability, which is the sand, propan permeability multiplied with width of the crack. Okay. Can you see my drawing there, boss?
Yes, sir.
Divide by formation permeability. This is the K of a propan. This is the formation permeability multiply with half length, the length. So if I draw it here, this is your well bore. This is the width. On the well bore, you pump down the high rate, you crack the rock. When the rock is cracked, then you start having the width. So this is the width here. While from here to here, going down to the reservoir, this is what we call half length, XF. Okay, let me slow down here. So here, guys, the top part of the equation, this is what we call K over propan. This is what we call conductivity. This part at the top, which is K of the propan, permeability of a propan times the width, is your conductivity. And the bottom here is your formation. The top part is a representative of your fracturing, this K prop and width. The bottom part is a representative of your reservoir. Imagine this, okay? Pay attention here, I mean, because this is important here, important concept. After this, if you understand these slides, you will be very easy to understand the whole fracturing concept. So let's go. Let's say you want to go to the airport, right? I don't know, or stadium. So or you wanna see you want to see a music concert or catch the flight. You go to the airport. Let's put it. Let's say let's call it. You want to go to the airport. Then you go with the highway from the house. So this is your airport. This is your airport. I don't have very good whiteboard here. This is your destination airport, right? And this is your home. You go with the highway here, right? But along the road, the way from the home to your airport, there is a supply road. Fill up the toll, fill up the highway, right? So maybe somebody, the A guy is coming from a different part, go join the tollway to go to the airport, and another guy from another area, this is B, coming again to a different gate to the airport, and so on and so on. So everybody come to this airport to go here. All right. Now, slowly. This toll is what we call conductivity. This toll road is a representative of your frac, or this is what we call conductivity, which is K the propan permeability, multiply with your width. The supply road here is your reservoir, which is this one here, the K of formation multiplied with the half length. So this is the supply road, okay? So looking at this concept, you will see that your toll number here cannot be less than your supply road. Agree or not? Because if your toll is less than supply road capability, then you will have a traffic jam in your toll. Let's say your toll can accommodate less cars going, but the supply road send 100 cars. What happened? 100 cars try to get into the toll road, but the toll road can only accommodate for 10 cars at the same time, at one time. Then there'll be a traffic jam in your toll road, okay? The other way around, and this is the FCD of anything less than 2, right? I mean, if your FCD is 1, then you supply one, toll road can supply 1 car, and then your supply road can as well deliver 1 car. So it's fine, but there is no, excuse me, there is no safety margin there. So the best number for your FCD is actually 2, which means 2 is what? 2 is your conductivity here, which is K propan times width, which is your tall, can deliver 2 cars, while your formation deliver 1 car. So you are in the safe mode, safe side here, that your tall will allow you to go to the airport without any delays because it's bigger than what the supply road can deliver, right? So that is the concept of FCD and conductivity and the skin, right? Imagine if you are at FCD of 1,000, what does it mean? When you have a FCD of 1,000, and put it into this analogy, the total and the cars. Raise hand and answer the question. What does it mean when my FCD is 1,000? Meaning you can deliver 1,000 cars, but at the same time, the supply road only sending 1 car. So wasted system, you just built the very big toll road in the middle of nowhere, in the middle of a desert maybe, that nobody get into that toll road from around. Okay, that's what does it mean. So anything, the FCD, the best FCD is anything bigger than 1 for sure. But again, it's not that too big, so then you actually wasted your resources when it comes to materials and works. You actually wasted your investment, your money, your value, right? Anybody clear on this one? I hope so. Just raise hand, right? Let me go back again. Now you see my screen mode again, my slideshow. Pause. Very good. All right, so let me continue again. So this propan permeability, this one here at the top, as I said, is your conductivity, your fracturing representative. And then there, at the bottom, here at the bottom is your reservoir representative. Your frac representative at the top has to go higher than your reservoir, because then you want to let your toll or your fracturing has to let more hydrocarbon move to the reservoir, move to the wellbore from whatever the reservoir can deliver, right? So I hope it's clear. Let me just erase one here and here continue. It's technology here by Schlumberger. If you guys interested, then you can ask me later on. But as of now, we skip. Okay. Fracturing operation. So now, if you go to the field and if you see any fracturing operation in the field, you heard anybody doing fracturing job. This is what plus minus you will see in the field. It's a lot of trucks, units, equipment going to the field. A lot of material as well, chemicals and everything move to the field for this fracturing job. The fracturing job maybe lasts between 30 minutes to maybe maximum half day or 1 day, right? It's not that much, but the preparation for the job takes a very, very long time. It can be 1 day, 2 days, or even a week or a month, right? In some remote location, you have to move all these trucks and unit and equipments maybe by helicopter, right? And you can see lots of truck. And this one truck is very high horsepower truck. It's 2,500 horsepower, right? Imagine you have like 2,500 horse. That is one truck, and you have 20 trucks here. Not talking about the weight. one truck can weigh like 30 tons. I'm not sure what unit you guys use, but 30 tons is 30,000 kilogram, right? So a massive operation, and everybody in the field will do this a very short job, concentrate on this short job uh, uh, with one command from the fan. So if you look at this one here, nobody's walking around during operation. Everybody has to stay either in their trucks, or if you work for oil company and becoming company man or oil and gas representative, you will stay here. This is the frac cabin, frac fan monitoring cabin, right? Nobody can walk around during operation, that 1 hour or one day of pumping, because it's very high pressure. Here on the treating line, you can easily see a 5,000 psi during pumping, and it's very scary, guys. I mean, very dramatic. When you start pumping here, sometimes this treating line is shaking the ground, shaking on top of the ground. It's like boom, 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 boom. You can see all this steel iron with the 5,000 pound in it, or even 10,000 pound in it, is shaking around. Imagine you cannot miss the safety factor and preparation for this job. Everything has to be pressure test and everything has to be right. You're not talking about the safety concern on this coming from the chemical too. Pressure is one thing, but then another thing in fracturing, you deal with lots of chemical, right? And this chemical can be dangerous. Some is dangerous, some is not. They are not as well, right? I mean, they are a very small portion, because 99% is actually water and only 1% is chemical. But again, if you are somehow exposed, your skin is exposed to this chemical, then you should like rub it or wash it gently with the water right away. You don't want to wait. Okay. So then now the fracturing operation, as you can see, all these trucks and everything, we have 500. We have a frac tanks. Frac tank is the tanks to collect, to store the 500 barrel of fracturing fluids. Usually you put it there. If I go back again here, all these yellow tanks here, it's a frac tank, all right? So you can see this small water truck here. This small water truck is to fill up the frac tank, the water tank. And then there is a sand container. Sand container is to store the sand and the proppant, right? So if you look at this long container here, this is the sand. You can see that there is a separation here. This is one side of the tank, and then there is second compartment, the third compartment, and the fourth compartment. So inside the tanks, they divide it into compartments, so they can open one compartment and then allow the sand to go in. So you have water here, water, and then you have sand. So the sand or the proppant is coming to here. This is this truck here, these two trucks here. We call it blender. We call this blender. So then the water is sucks to the blender, the gelling water is sucks to the blender, and the proppant as well pour to the blender. And the blender will mix these fluids and proppant together and send it to the pumps. So if you look at all these pumps here, this is all the pumps. The pumps then will send that slurry, we call it slurry, which is slurry of water, a gel, fracturing fluid, and the proppant to the wellhead, right? So this is water again. This is water, this is sand. They are mixed in blender. From the blender, they are sent to the line, and then the pumpers, this is all the pumpers, will send with the high pressure and high rate to the wellhead, and this is the wellhead somewhere here, right? Because we are pumping at a high rate, then we crack the rock and then fill it with this fracturing fluid and proppant, right? So there is a blender. There is a pumpers as well, 2,000 500 horsepower of a pumpers. And there is a frac monitoring cabin, and then treating lines for you. The 3-inch treating line is for you to pass this to pump this material and fluids to the wellbore. All right. Again, if you have any question, raise your hand. So then it's very
Yes, sir.
complicated. I'm just yes.
One of our participant, Arvind Raj, he's asking a question,
Yeah.
and his question is based on FCD formula. Does that mean a shorter half length corresponds to better FCD?
Okay, fine. So, all right, let me just answer that very shortly, very quick. Let me go back again to FCD here. All right. So look at this for the question. If you look at this formation permeability here, right? If you're dealing with the high permeability, first of all, you want to have a good FCD. Everybody agree on this, right? You want to have at least two FCD of 2. So if your FCD is 2, then you will end up here, right? At the very good drop of a skin. If you're dealing, but the FCD is, you have to play around with these 4 parameters, the proppant permeability, fracturing width, fracturing length, and formation permeability. Your question is, to improve your FCD, should I go with the short length or not? It is not, because that depends on your formation permeability. Imagine this, if you have permeability of 1000 here, what does it mean? Is it difficult or not for you to get high FCD? Let's say you deal with the high permeability formation and you have 1000 here. Of course, the whole thing here is divided by 1000, right? And it's very hard for you to get FCD correct. So in this case, you really want to move your FCD high by having the width up. Agree or not? Permeability up, while the length down. When you deal with a very high permeability, let's say 1000, the whole thing here is divided by 1000. So you have to have width up, proppant permeability up, a bigger proppant, so then the permeability is higher, and then the short length. Length is small, all right? By doing this, then you can optimize your FCD. However, let's take a look another case here. Where is my eraser? If you deal with a different scenario, let's say you deal with the formation permeability 0. Sorry, where is my draw? Let's say this. Okay, 1 minute. Somehow I have a problem here. Erase. All right, so let's say you have formation permeability of 0.001. All right. If you deal with the nano permeability here, 0.01, what does it mean? How do you improve your FCD? It's very easy, because everything here is multiplied by 1000. Agree or not, host, at least? You divide everything by 0.001, meaning that you multiply the whole things with 1000, right? X divided by 0.01 is similar with X times 1000. What does it mean? So in this particular case, your permeability, because it's very easy to get the high FCD, then because it's very easy to get the high FCD when you do with a very low permeability reservoir, then your permeability can be actually low. Your fracturing width can be a bit less, and your length can be very long. Okay? You can choose a small proppant, so then permeability is low, or very tiny width, but the keyword is a very long length, fracturing length. So you can reach more reservoir, deeper to the reservoir. Because why? Because you have a luxury of multiplication by 1000 when you do with the low reservoir permeability. Okay? So that's my short answer. So let me just continue we can talk about about this later on during a question and answer. So let me just continue with my presentation. So now you're dealing with a very massive operation in the field, and that I can say that this is one of the most expensive operation in oil field. Okay, fracturing, because it can be 100K, 100,000 US dollar, or even when I was in Middle East, the job cost can be like 500,000 US dollar. That is for 1 or 2 hours pumping, right? Imagine 2 hours pumping, 700,000 US dollar as a cost of a frac job in Middle East, for example, right? In some of our client. So then, if you go with here, it has to be prepared very carefully, not only on the operation side, but also in your design. Because if you have a very bad design, not only that you can affect the production, you don't achieve what your production expectation, but also at the same time, you can ruin your operation as well, i.e., your job is stopped in the middle of execution because of miscalculated on parameters, and then you have what we call screen out, right? So then, when you talk about data requirement from the reservoir point of view, you will need all these data component. You will need the numbers of what is the permeability. After that, you need a geology. You want to make sure that your rocks is far from the fault, your well is far from the faults, and you know all these geology features around your wellbore or well. Then collect all these logs that you have, open hole logs, and then quantify if you have water nearby zone and everything. You have if you have a good uh, if you have enough money, you can also run a sonic scanner and GSI log to understand some of geomechanic natures like young modulus or even stress. You can develop the stress profile for your frac job, right? Reserve, of course. You've been a long way to do all this technical work, but if your well has no hydrocarbon, what's the point of doing all this fancy treatment, right? So you first of all you have to make sure that you still have a reserve hydrocarbon in your reservoir before you try your best to take them out. Okay, and that's from the reservoir point of view. Now there is a completion as well. Completion is something that you can design, right? Then you need to know what's the depth, what's the wellbore diagram, perforation detail, wellhead configuration, and as well water source. Water source is you're going to use for the job, right? So candidate selection and production. All right. So let me draw something here. Let me just again new share here. Stop share or new share. Stop share. Okay, fine. So this is important for you to understand, or which is not in the slides. How do you choose the best treatment for your, the best stimulation treatment for your reservoir, right? So number one, so number one, you start with lithology. So you have a lithology here, lithology, and let me just put this lithology into two. Number one is sandstone, and the second type of it is carbonate. Carbonate. Forgive my bad writing here, but let me just spell it. Sandstone and carbonates, all right? So under sandstone, you have two types here. Number one is you have low permeability. Okay, my notation is K is permeability, all right, guys? And number two is you have, of course, high permeability. Then under carbonate, you have a similar situation. Low K, and high K. Right. So look at this. if you're dealing with the sandstone, remember, sandstone, they don't react with the acid. Sandstone don't react with the acid. So if you deal with the high permeability sandstone, you just want to remove your near well bore. What you pump here is what we call matrix acidizing, matrix treatment, matrix with the mud acid. Mud acid. So this is mud is MUD acid, right? Matrix acidizing with mud acid, not with the HCl. Okay. Now, when you deal with the low permeability sandstone, then you don't have any other option but to proppant fracturing. You prop frac, we call it prop frac, right? Now, let's move to the carbonates. When you deal with the carbonates, you have high permeability carbonate. You can do acid, which is simple acid, HCl. So this is matrix acidizing type, matrix acidizing HCl, all right? While here for sandstone, if you remember, matrix acidizing but with mud acid. Now, when you deal with the carbonate low permeability, you have two options here. Number one is acid frac. Acid frac, and you still, all right, good. And number two is prop frac. Prop frac. But remember the one that I explained before. Prop frac, because this is low permeability, this will be a long half length, right? Because FCD is okay, long half length. All right. So again, let me just go through again this chart here. Based on your lithology, you have sandstone and carbonate. Let me start with sandstone. When you deal with the sandstone reservoir and you deal with the low permeability, your option is proppant fracturing for the stimulation, right? When you deal with the high permeability formation, your option is matrix acidizing with mud acid, all right? Now you deal with the carbonate. When you deal with the carbonate reservoir, low permeability, you have two options, acid fracturing when the solubility is good, or proppant fracturing with a long half length, right? Now, with the high permeability, then you can do matrix acidizing. Let me add something here. On your sandstone here, if you deal with the high permeability, not only you can do matrix acidizing, but you can also do the proppant fracturing, prop frac, but short half length. Remember that TSO, short half length. Okay. All right, guys. So two slides, two very important slides from my presentation is the number one is the FCD concept, and number two of this candidate selection. All right. So this can be your. Forgive my bad writing here, but again, I hope I explained the whole things clearly here. Right. Any question before I move back to the slides again?
Yes, sir.
Anybody?
Am I audible, sir?
Say it again.
Dr. D.K. Gupta, sir, from Department of Petroleum and Energy Studies, UPS, has one question.
Right.
And his question is, how minimum horizontal stress affect fracturing?
What is the minimum horizontal is affect fracturing? All right, fine. Let me just go through this. I think this session is recorded. Am I right or not, host?
Yes, sir.
All right, good. Because I will erase this, right? So there are three states of a stress. Thank you for the question. Again, there are three states of a stress. This is the state of a stress. This is what we call P. Can you see it? Okay, fine. P overburden. And this is what we call minimum horizontal stress, and this is maximum horizontal stress. So at this point here, at the rock, you have a overburden pushing this way, you have minimum horizontal stress here and maximum horizontal stress on the other sides, perpendicular to it. So what happens when you frac, right? You actually open your width perpendicular against the minimum horizontal stress, right? So in fracturing, what important is this guy here, minimum horizontal stress. This is what we call minimum horizontal stress, or what we or commonly called closer pressure, P closer, or people call it as well minimum in situ stress. In situ stress, or minimum principal stress. So many terminology for this principal stress, right? A frac guy, we call it closer stress, right? Closer pressure, right? So this is the minimum institutional stress. And how do you define this minimum institutional stress? Because it's very important. At the end of the day, width, let me just go here. I think I will go deeper a little bit here. If you remember FTD, we have a width. Width is equal to, how do you get a width? Width is equal to P net pressure, times fracture compliance. We call it fracture compliance. Fracture compliance is a function of Young modulus. Now, while the net pressure here, equation P net is equal to pressure minus P closer. This is the P closer here. So when you have a bottom hole pressure more than closer pressure, then you start having the net pressure. So you apply stress, right, to the rock. You crack the rock like this. You apply, and then at some point, your rock will fail. It start to crack, right? When your rock is start to crack like this, you start developing the width. This is your width against the minimum in situ stress. This is your minimum in situ stress like this, because then your width can only be open when it fight against your minimum in situ stress, not the maximum one. Now, when you have this, meaning what? The bottom hole pressure that you send from the pumpers on your surface, now above the closer pressure, and then you manage to crack it. When you start to crack it like this, then the difference between your bottom hole pressure and the closer pressure that tried to close it is what we call net pressure. So the net pressure is the pressure inside your fracturing. Now, when you have a pressure inside your fracturing positive, then you start having a width. And that is why your closer pressure is very important, if that answers the question. Now, let me continue. Knowing that this closer pressure is important, how do you get this closer pressure value, minimum? There is some approach can be as simple as your PC is equal to your P overburden plus 2P reservoir pressure divided by 3. Okay, that is the very easiest, one of the easiest equation. Or there is another way, is 1.5 times your closer pressure is equal to P closer equal to 1.5 times your P reservoir. And of course, there is a complete way to calculate based on the Young modulus and Poisson ratio. All right. So there is a complex way to do it as well. But 80% of the rock in the world, you will satisfy with this approach here to calculate reservoir pressure, either 1.5 times of your reservoir pressure, or overburden times 2 times P reservoir divided by, you will get estimate of your closer pressure. I will say 80%. Okay. I hope that's answered the question. All right, so let me continue with the presentation here. We are like 1 hour, 15 minutes already. Let me just continue here. You have 2 good slides already. Now let me just continue the rest. This is the good fracturing candidates. Number 1, of course, that the benefit from the simulation. You don't want to choose the well that doesn't make any production increase. Whatever the production increase, if you have a couple of wells, choose the best one and the highest production increase as possible that you can do, right? And you have low permeability, you don't have option, right? In US, for example, if you're pumping a shale gas, for example, you want to drill the shale gas reservoir, you don't have any other option but to frack it, because if you want to have it flow naturally, it's impossible, right? Super extra low permeability, you need to frack it. You have to frack it. That is why all the shale gas and shale oil development in US and other part of the world, they are using horizontal wells completion and then multi-stage frac to it, right? So one horizontal well maybe 3,000 feet, and then they put like 10 stages or 20 stages to it, right? Strong barriers above and below the pay zone, enough drainage radius, and as well enough reservoir pressure and high hydrocarbon saturation, right? The bad candidates when you don't have a saving, reserve is not there, right? You don't want to do it. A very low reservoir pressure. When I said a very low reservoir pressure, maybe you come to me and then ask, hey, I will put artificial lift at the end of the day after the frac job anyway. No, it's not. That's not the point. The point is, yes, you will put an artificial lift, but again, your penetration is deeper to the reservoir. You are pumping a frac fluid, which is a damage to some extent, right? So if you don't have a good reservoir pressure to bring back all this damage from the frac fluid to the wellbore, though you put the artificial lift at the wellbore, then you are not having a good fracturing job, I will say, right? And how low is low reservoir pressure? I will say anything less than 0.2 psi a foot, I will say don't try. Find anything above 0.2 psi a foot. I mean, I'm fracking for the last 23 years. I cannot get a good result when I deal with 0.2 and less psi a foot reservoir pressure, right? While the other option, when you have a higher reservoir pressure a bit, then it's good. When we call it low or high, it's always based on the water, right? Water is 0.43 psi a foot, so anything less than 0.43 psi a foot is low. Anything higher is high. But when it's lower than 0.2, then it's extremely low, I will say, right? So then there is a wellbore integrity issue as well. If you have a wellbore integrity issue, casing leak, tubing leak, packer leak, anything leak, old completion, you don't know even the depth of your packer and everything, don't do it. Pull out everything and then put the new completion, okay? Strong water supply, if you have a water zone, don't do it, because if your frac break to the water, you're not gonna only produce oil, but you also will produce a well with a high water cut. In some situation, it is not preferred at all, right? And soil formation, when you deal with the soil formation, i.e. low young modulus, then it's very hard to generate the frac width and then as well to provide a good conductivity at the end, right? And last but not least is completion. You have a screen, you have gravel frac completion, that's not good, right? Now, what's a comparison? You see all this good skin and everything, but physically speaking, what's the comparison of a frac? If you have a vertical well without frac, this is on your left side here, right? Then you put the horizontal well. When you put the frac to your vertical well, that is 270 times here. If you see this annotation here. So here, when you have vertical well and you frac it, this is 270 times with the well without frac. Okay, this is a contact area. And when you have this horizontal plus multiple stages frac to it, then you actually have 1,100 times of your vertical well without frac. right? So that is the power of a frac. I would say that's a number. The number is 2,700, 270 times of a frac contact area when compared with a vertical well without frac, right? And that is how frac can reach more reservoir contact and can improve production as well, other than all these skin and FCD and stuff that we're talking about just now, all right? Continue there with, how do you out from here? Erase. Fault of increase is the production after divided by production before. So this is the equation to it. RE is reservoir radius, RW is wellbore radius plus skin divided by if you look at this here at the bottom is RW absence, which is the half length as well, because half length is acting as a new wellbore radius, right? Fracturing material, guys, a little bit more. So we have a frac fluid which has viscosity of 100 centipoise. Why you need a viscosity of your fracturing fluid? Because you need to carry the propan. The propan is the sand. Without a viscosity, then the sand will be dropped when you're pumping it, right? You cannot bring this propan to your fractures. So you need a viscous fluid to be able to bring all these sands and propan to your reservoir, right? And India is one of the best place, best produce gel in the world, right? I mean, guar, to make the frac fluid viscose, you need guar, and guar is, I think, if I'm not mistaken, I'm sorry if I misspell it, is come from the area called Rajasthan, right? So that is type of desert, and Texas, Houston, Texas in USA try to copy that. They get the seeds from India, try to have it in the Texas desert, but again, they cannot match the quality of guar coming from India, right? So what need to be done? Make sure that everything is good. Location, go to the location, check the water for you to make a viscous gel. Put the bactericide to make sure that the water is clean. Checking all connection. Pressure test all the lines one by one. Remember, your line is maybe fill up with 5,000, 7,000, or 10,000 pounds easily when you are pumping, right? So material inventory, lighting, fuel, and other party. Economic, of course. At the end of the day, a few people do this for fun. I do frac for fun. I love to frac. I enjoy being in the field, smell all this diesel, and hearing all the scream of every pumpers, right? But again, there at the top, and as well for us, we need to understand the economic as well, right? I mean, a frac job is one of the expensive one, and you have to make sure even before you can produce a good hydrocarbon production to be able to pay all these fracturing job costs, right? A normal team payout time may be between 1 or 3 months can be used. I think it's very fair, right? So that's the end of my presentation. So if you guys have any question, go ahead.
Yes, sir.
Yes,
How
go
does
ahead.
salt movement affect the fracking in salt zone?
How is the what? I'm sorry.
Salt movement affect the fracking.
Salt movement. Can you just type it maybe? I'm sorry, I missed that
Okay,
terms.
sir.
Yeah,
Sure, sir.
type in the chat. Other
Sure,
than
sir.
that, maybe if you have Ricky Sanjaya, if, just let everybody that raise hand to answer.
Sure, sir.
I have Lewis and Ricky Sanjaya.
Okay,
Raise
thank
hand.
you, Mas Yando,
Go
for
ahead.
the opportunity, and thank you for the host as well. Mas Yando,
Yes.
before we need to frac, we have to design it first, right? How do you design how much fracturing fluid volume and propan we need based on the depth we have? I know it all goes to the simulation first, but is there any rule of thumb or equation that might have to do for the initial design? Thank you, Mas Yando.
All right. first of all, Rizky, are you there in India now?
No, I watched your previous presentation in IATMI Pusat, Mas Yando.
Okay. All right. So if you are here, guys, this is your reservoir log, right? So if this is your log here, and this is your shale, and this is your net pay, the one that you want to frac, right? So your net pay here, maybe you have a height, right? Maybe this is height. Your height may be 100 feet, all right? So again, rule of thumb, if you design a frac job, let's say low permeability, if you deal with the low K permeability reservoir, then you pump 3,000 pound, 3,000 pound per feet. If you deal with the high permeability, then you may pump 1,500 pound per feet. Okay, meaning that if you deal with 100 feet of reservoir, then you're pumping and low permeability, then you're pumping 3,000 times 100, then you're pumping proppant of 300,000 pound of our proppant. If you deal with the high permeability, maybe 100 feet permeability, 100 millidarcy permeability, then 100 times 1,500, then you may want to pump 150,000 pound of propane, right? As well as the frac fluid, of course, is there is another cost. Risky, I cannot cover that here. I mean, it's based on the propane concentration and everything. Okay. Next question, Luis. Luis, go ahead. Luis or Ayush Pandey. There is hand here, host. Can you let?
Yes, sir. It will take us some.
Okay.
Hello, sir.
Yes.
So my question is that, so can you explain about self-suspending propellants, and would it would be more economical than ceramic propellants, which is mostly used in fracking?
All right. So, okay, the self-suspended propellant, right? So if you remember what I said, that I need the fluid viscosity to be able to carry the propellant, otherwise the propellant can drop and settle, right? I mean, the propellant company, which is like Carbo or St. Joseph's or anything from Europe, US and China, they develop what they call lightweight propellant. It's a very lightweight. It can be half of the typical ceramic propellant, right? Very light. So then, because it's light, then you don't need a very viscous fluid to carry this propellant, right? So, so this lightweight propellant, because it's lightweight, then you less viscosity to bring it, and then you can go deeper to the formation. When you don't need a lots of viscosity of a frac fluid, that will help your operation. It will be less pressure, less damage, because the gel that you are pumping is going to be less too, right? I mean, so there in the industry, right? It's more it is more expensive, but it is what it is. It's available, right? If you ask me, is it better than ceramic? Many times when it's applicable, yes, it is better than ceramic propellant or heavyweight propellant, right? Next question. I have Luis, Nandini, Aruz, Batuya.
Can you hear me?
Luis.
Okay, thank you. And thank you for your presentation, very informative.
Yes,
My question is regarding to closure pressure. So
yes.
you presented to us two correlations, right? But from your experience, is it required also to apply any extended leg of test previously in order to have more accurate data to performance any hydraulic fracturing, or you see that by using correlation is enough?
Okay, let me answer that. So again, the closer pressure that we are using is assumption. Okay, is in assumption. You assume that, hey, my assumption, my closer pressure is equal to 1.5 times of P reservoir. This is assumption. Okay, this assumption has to be validated by what? By what we call mini frac. So mini frac is a service that you are pumping before the main frac. You are pumping with a high rate, with the frac fluid and everything. Then from the leak of from the decline analysis, later on there is a G function here. This is what we call G function. Okay, then you will decide which one is the actual closer. So let's say actual closer pressure is here, then you actually have to modify your design, which is previously assumed with that one. Now, if you ask me, can the extended leak of test helps on this to define this closer pressure? I will answer. My answer is yes or no. I mean, standard leak of test, you will help to get the accurate reservoir pressure, right? When you have an accurate reservoir pressure, then you will have a better understanding of your reservoir pressure, and you can apply that to here. Okay, uh, that's my answer. But if you ask me, can I get the direct closer pressure but having a longer leak of test? No, you don't. Right? So no, you don't. You will get having a longer leak of test, you will get the better reservoir pressure because then you will reach your radial flow higher chance when compared with very short leak of test or decline, right? Okay, next question.
Okay, thank you.
Hi, sir. It was a great session. First of all, thank you. My question is that we have different type of completions for fracking, like pinpoint frac or limited entry frac. So how do we decide which one to go for?
All right, completion, frac completion is actually has to be the best frac completion is the most simplest one. That's the best one, right? Because then you deal with the lots of pressure. If your completion is complicated, then you will have lots of pressure loss and everything, right? But now, if you ask me about limited entry is designed for something, right? Limited entry, every completion is designed for something. You may want to design for diversion, right? You may want to design the uh, completion or perforation to be able to break the rock when you deal with the very hard rock, like when I was in Oman, or diversion, limited perforation, limited uh, and range of a short perforation when you deal with the horizontal wells and everything. So talking about diversion, yes, playing around with the limited entry and everything is good, right? I mean, again, not only that, you need to have a knowledge on other part like a stress, contrast, and everything in the various way. But again, the best completion for frac is the simplest one. Remember that, right?
Thank you, sir.
Yes. Next question.
How
Anuj
can we
Bhatia.
determine how can we determine the width loss due to the spurt losses and leak off?
Okay. So this is a bit detailed here. I try to simplify my explanation, but again, to answer that question, we can have another session. First of all, there is a leak off. Leak off, there are two types of a leak off. The simplest one, there are actually four, but if I can define two of them, leak off, there is first of all, there is spurt, like you mentioned, right? And then after that, there is a leak off, standard leak off during pumping and during decline, okay? Your question is specifically for spurt. When you do a mini frac analysis, spurt is actually assumed as 0. What is spurt? Spurt is you crack the rock, right? You crack the rock and the rock is open like this. Spurt is a leak off to the frac face wall to the frac wall before the gel is controlling, stick to it to the wall and then control the leak off. So spurt is exponential leak off, I will say, right? But then our assumption in fracturing analysis, you assume spurt of 0, meaning what? Meaning by the time you crack it, your frac fluid is arrived and then control the leak off to the fracture face and create this fracture face skin, we call it, right? So then, how do you define a leak off? Leak off in fracturing, why it is important? Leak off is important as to design a frac job later on, because leak off will define what we call fluid efficiency. Fluid efficiency is defined by frac volume divided by fluid injected. Fluid injected. So you're pumping fluid like let's say 1,000 barrel, and then your fluid volume, fluid, the fluid injected is 1,000 barrel, and then fluid efficiency, this is FE, fluid efficiency, let's say 30%. What does it mean? If you're pumping 1,000 barrel of fluid from your surface, from your frac tank, and you only have a 30% fluid efficiency, your frac volume is what? 300 barrel. You're pumping 1,000, but fluid efficiency only is 30%. So 30% of 1,000 is 300 barrels. So your frac volume is only 300 barrel. Where is the remaining 700 barrel? Leaking off to the formation. It's gone to the formation, leak off while you are pumping. Though you have a skin here, fracture face skin here is developed, still you cannot control the pressure coming from your pump at the same time, a fracturing fluid viscosity and your formation fluid viscosity that control the leak off. The 700 barrel is gone. Now, what is the terminology for it? Is this 30%. If you deal with the fluid efficiency more than 30%, if it is more than 30%, what does it mean? You deal with what? You deal with the 50%, you deal with the low permeability formation. Why? Because it only allow very small amount of fluid to go. But if you deal with the less than 30%, let's say 10% fluid efficiency, you deal with what? You deal with the high permeability. Imagine you are pumping 1,000 barrel. Sorry. You are pumping 1,000 barrel, and then your fluid efficiency is only 10%. Your frac volume is only 100 barrel, and remaining 900 barrel is gone to formation, leaking off. Meaning that, hey, why is 900 barrel is gone, and at the end I only have 100 barrel of a frac volume? Because your formation permeability is high and let all this frac leak off so high, and then let the frac volume is so low. All right, so that's the answer to the question. Leak off is important. Spurt is assumed at 0. If you deal with the screen out or excessive leak off later on, then you have to investigate the spurt. Maybe it's not 0, your assumption is wrong. But at the end of the day, even the spurt is 0, your leak off with fluid efficiency correlation is what I explained here. The higher the fluid efficiency, the less permeability your formation is. All right. Next question is becoming less people here, 61. All right. I think I pick up another 1 or 2 questions more, if you guys don't mind.
I do have one more question.
Okay.
Yeah, actually, I wanted to know more about Schlumberger highway frac technology.
All right. So, I think I have simulation, but you know what? I have simulation. I'll also wait to you later. But again, Highway is if you're pumping a frac job, you are pumping fluids and propane at and all this fluid and propane will fill up your frac volume here. With the highway is different. Highway you are pumping propane and fiber. You are pumping propane, fiber, propane, fiber. So what does it mean? This fiber is dissolvable fiber. So the moment you finish your frac job, in between the propane chunk, you have this fiber that is dissolved. So at the end of the volume, the road, the width of your frac to allow the hydrocarbon to move is actually infinite, because you have infinite conductivity. You have infinite conductivity with the highway because of all this road that created by dissolvable fiber, right? So there is a use of a fiber in highway technology. So highway is the best Schlumberger's new technology, not only in fracturing but also against the waterline and everything revenue in terms of application. It's been in study or in the R&D for 8 years, 7 years secretly before it's released to the industry. And it's 8 years, and I think now everybody in the industry, after the patent is gone, they start raising their hand and then say that, hey, I have highway as well. I have no, I can do highway too. Everybody raise hand. But the concept is, you try to connect with it, right? Go ahead. Any other question? All right, host. I think we have a good 1 hour 45 minutes here with my presentation and question and answer, and I really hope that I somehow sharing some knowledge to everybody here that may be beneficial for your future, hopefully. All right. If there is no more
Sure, sir.
question, then maybe we can end up the session.
Thank you so much, sir, for giving us your valuable time. This insightful session has helped our budding engineers establish a broader perspective of fundamentals in hydraulic fracturing. The objectives we learned today have certainly strengthened our concepts. Thank you everyone for attending the guest lecture. Please send your name and email address to the host for the certificate of participation. I would like to thank faculties who have joined us here today. Dr. Uday Bhan, our faculty advisor, Dr. D.K. Gupta, Dr. Annapurna Borua, and Dr. Pushpa Sharma from Department of Petroleum Engineering and Earth Sciences, UPS, for gracing us with their presence in today's session. I would also like to thank Mr. Taranpreet Singh and Mr. Siddhant Chadda, respected alumni of UPS AAPG Student Chapter, for their presence in the session today.